This webinar is hosted by Atlantic Arctic Cooperation Network and Women in Renewable Energy. My name is Maya Falvo, and I'm Communications Manager, a part of the Advisory Committee at Women in Renewable Energy. I know we have attendees from all over the world today, so it would be interesting to hear where everyone is calling in from. If you don't mind putting that in the chat, I will start. I am in Montreal, Canada. At the end of the webinar, we will have a Q&A session, but you're free to put any questions you have in the chat throughout the webinar, and either we will pick them up at the end or we will try to answer them throughout the webinar directly in the chat. Today, we will take a practical look at how we can harness clean energy from space. In particular, we will explore how space-based solar technology can help address energy challenges in remote areas such as the Arctic. We will hear from a great panel of speakers working in this field, discussing the opportunities and challenges that space-based solar energy represents. But before jumping into the webinar, I will tell you all a little bit about WIRE, also known as Women in Renewable Energy. WIRE is a nonprofit organization with the purpose of advancing the role and recognition of women and other underrepresented groups in the energy sector. We were founded in 2013 in Toronto, Canada, and we have now grown to have chapters all over the world in Africa, Asia, Europe, and Americas. Our programming consists of a range of different activities. We have networking meetups, workshops, field trips, speed mentoring, and we also offer a lot of webinars and online events, such as this one here. We're also actively working with partners and sponsors to fulfill our mission. So, how can you engage with WIRE? If you would like to get involved, we're always looking for volunteers to help us fulfill our mission, both in Canada and internationally. So you can go to our website, womeninrenewableenergy.ca, and you'll find a sign-up button there to join as a volunteer. You can also connect with us on our different social media accounts, such as Facebook, LinkedIn, YouTube, and Instagram. And with that, I will hand it over to my co-host from ICN, Fredrik Thorsen.
Thank you, Maya, and welcome everyone. Let me just quickly share my screen here. My name is Fredrik Thorsen. I am the project manager and deputy director of the Icelandic Arctic Cooperation Network, and the proud co-host of this exciting webinar discussion. Now, before we start, I would like to take a moment to offer an extremely brief insight into who we are as an organization. I would say that the ICN is best described as a collaborative platform. We are comprised of some 28 member organizations, which range from universities, governmental organizations, NGOs, research institutions, and industry, which itself it aims to initiate, encourage, and facilitate cooperation on Arctic issues. And as I hope you can see, in this task, we participate in a vast variety of projects. And just to mention a few, some of these include the Arctic Council Working Group Project, Gender Equality in the Arctic, as well as the Share Your Not platform on which webinars such as these are hosted. We also provide consultation and co-produce knowledge for the development of implementation of policy. And we also work to organize Arctic-related events, such as the upcoming Arctic Plastic Symposium, the West Nordic Research Managers Platform, and of course, this very webinar series on renewable energy in the Arctic. Now, it has been my pleasure to have worked with WIRE on this installment, and as well to introduce today's moderator and my good friend, Heather Alonsdottir, lecturer and researcher of space law at Birkbeck University of London.
Thank you very much for that very kind introduction. So I'm Dr. Heather Alonsdottir. So I'm an academic of law. I teach at Birkbeck University in London, previously taught at Bifröst University in Iceland, which is where my Arctic connection comes from. And I have a forthcoming book called New Perspectives in Outer Space Law coming out later this year. So I'm here to moderate the session. So we'll firstly do questions from myself to to the panelists, then we'll open it up to the audience as a whole, for which I'll moderate that. So I'll just very briefly introduce our speakers today, and apologize again for my technical glitch at the start there. So firstly, to introduce and give a very warm welcome to Sam Adlin, who's the co-CEO of Space Solar. I believe we'll be hearing from him first, and he can introduce a bit more of what Space Solar does. It's very exciting and innovative company. Then we'll hear from Dr. Karen Hinze, who's the Vice Dean of Research at the Faculty of Engineering and a professor at the School of Electrical Engineering and Computer Science at the University of Ottawa, and hear her very interesting perspectives on this. And then thirdly, we'll hear from John Mankins, the founder and CEO of Mankins Space Technology, which is also doing very exciting work in this arena. So without any further ado, we'll pass over to them, but I'll be here in the background as a moderator, I think without any further technical issues, and then opening it up to the audience as a whole, because we're also very, very keen to hear your questions and perspectives on this discussion as well. So without any further ado, I pass over to the speakers.
Thank you, Heather. John, I think John was going to go first and do a little bit of an intro to space-based solar power. I'm going to come after John.
Yep, I'm all ready. Thank you, Sam. So good morning from California. I'd like to offer some thoughts regarding the status of space solar power. It's a pleasure to speak here at this jointly organized webinar. I confess I had not heard of the Women in Renewable Energy before this, and it's delightful to have the opportunity. So this is just a high-level overview of the concept. It's a very simple idea. There is practically limitless energy for the next billion years or so coming from the sun and passing by the Earth in space nearby. If you go to space and you harvest that energy with a large solar-powered satellite, known as an SPS, you can convert the sunlight into electricity and then transmit it using wireless energy transfer means, typically with a microwave at low intensity, to ground stations where it then gets translated just like energy coming from a terrestrial solar array into existing or new infrastructure, i.e. power grids and energy storage systems, and from there into the marketplace. So it's a very straightforward approach. The physics, as I'll illustrate in a few minutes, is really straightforward and is long since proved, but the implementation has historically been rather expensive, and this is the challenge for modern and modular space solar power. This is a particular example, the SPS alpha concept, solar power satellite by means of arbitrarily large phased array. That was my invention some years ago. The system comprises several major assemblies, an energy conversion array at the base. On the front, that's the gold panel, which is the wireless power transmission system. On the back of that is a modular photovoltaic array, then a structural system going up to the upper side, the up end of the solar power satellite, some wings that comprise a large number of low mass thin film heliostats that then redirect the sunlight as it comes in from different angles to the photovoltaic arrays. And this overall system involves a very large number of rather small modules. So although it is in toto a large system comprising on the order of about 5 million kilograms, approximately 5 or 6 million kilograms, and about 1 million modules. As you can do the calculation for yourself, the mass per module on average is on the order of 5 or 6 kilograms per module. So it's a very large number of small sats that are fabricated at low cost and then assembled in space using automated or telesupervised robotic assembly. So that's the basic concept of SPS Alpha. It can provide power essentially constantly. This particular platform is sized to deliver 1,000 megawatts or 1 gigawatt and would have a lifetime of some 45 years. The end-to-end efficiency is about 16 or 17%. The overall cost is about $10 billion, and the cost of the electricity generated by this particular version of the system would be about 6 cents a kilowatt hour, give or take a little bit. So, and at that price point, the cost of solar power from space should be quite tractable for most markets. This is a comparison of SPS Alpha and other modern modular designs in a single chart tabulated with data from Lazard's 2025 energy assessment, as well as some other references. And what you can see is that space solar power here in the lower right is one of the least expensive per kilowatt hour solutions to large-scale energy on Earth, and it is the lowest cost of those which are base load, essentially providing power on demand, which is dispatchable and as needed. I wanted to illustrate one concept, which is how space solar power can be implemented for the benefit of Arctic regions. And this illustration, this video, shows SPS Alpha, a constellation of them, some 9 satellites in geosynchronous Earth orbit, not on the equator, not GEO, but GSO. And during the course of a 24-hour day, the satellites move around in their orbit and see below them different local targets on Earth. And this means a single business, if you will, with a number of satellites would be able to deliver energy during the course of 24 hours, either to the southern hemisphere or the northern hemisphere, either on the equator or to the Arctic or Antarctic regions. And hence, a single integrated technical solution might meet the needs of customers around the globe, including the poles of the globe. Lastly, I wanted to just highlight one last little tidbit. So just to prove that space solar power is more feasible, I've included here a photograph of a demonstration that was done by some students at the Naval Research Laboratory a number of years ago. And what you see on the left is an end-to-end demonstration with a light bulb for an artificial sun, photovoltaic cells, a wireless power transmitter, and a wireless power receiver at microwave frequencies, about 2.45 gigahertz, down at the base being held by a good friend. I think it's being held by Paul Jaffe. But in any event, the main point being here that the physics of space solar power is completely established and has been for decades. Anybody can do it. It's not like other very advanced energy options that require massive investments just to prove the physics. All of the efforts that are being done today in modern and modular space solar power, and you're going to hear more about one of those in a moment, are dedicated to developing the technologies and establishing the economics of the resulting system. So that's it for me. Thank you very much. I hope I didn't go over.
That was wonderful. Thank you so much, John. That was really, really informative and provided a really, really great insights. I think we're next hearing from Sam. So I'll hand over to him now.
Thanks, Heather. And thanks for the great introduction, John. So I'm going to build on everything that John's introduced, and to talk specifically about some of the things we're doing at Space Solar, and also the importance of activities we've got towards the Arctic and polar regions more broadly. So I'm Sam Adler, I'm co-founder and co-CEO of Space Solar, where we're developing and commercializing space-based solar power. My career's entirely been in uses of space that benefit Earth, and really this is the ultimate in terms of that. So we've got some big challenges ahead in terms of energy demand. I mean, people until probably 6 months ago used to talk about energy demand doubling by 2050, and that was always going to be challenging. Even that equated to the equivalent of a nuclear power station a week, or something like 100 square kilometers of solar panels every day. And now the onset of AI and data centers, etc., we're now talking about quadrupling by 2050, and the challenges we've got with intermittent renewables in terms of nighttime weather, storage that doesn't exist at the scale or duration that's required, in the orders of magnitude increases that needed in minerals and mining. We really need new innovation in clean energy technologies, and space solar and space solar power absolutely provide that. There aren't many technologies that really can provide both the affordability, the reliability, and the scalability, and that's where space solar power really comes to the fore. And organizations like the World Economic Forum are now starting to talk about the importance of being able to put up those gigawatts per year per unit of critical minerals, because of the challenges we're seeing there. And the challenges at a global scale obviously apply even more acutely in the Arctic and high latitudes, with some of the extreme environments and the lack of grid connectivity. So John's kind of touched on this. I mean, there's a little bit of a why now thing, because this is not a new concept. It's been around since the 90s. Well, it was an Isaac Asimov idea from 1941. There have been engineered designs ever since the 1960s. But actually, it's the change in launch costs would have dropped by 90% and expected to drop even further, that now mean that it's both economically as well as technically feasible. It's always been considered technically feasible. And there's the original Isaac Asimov comic that we have in our office. And things are really developing very, very quickly. There's programs of scale now in the US, China, Japan. The UK's got big activity as well. So in China, they're talking about high-powered demonstrators by 2030. They're talking about kilometer scale arrays in space by 2028. Japan's got a demonstration mission next year. They're really strong in wireless power transmission, and then the US has been mainly funding stuff through defense and the DoD. But it's really kicking off now in terms of some of the private companies. There's been about $100 million of private capital gone into space solar power companies, predominantly those doing laser space-based solar power, where you get smaller ground footprint than what I'm going to talk about, and it's good for power but you can't deliver it at scale due to safety issues and some of the conversion challenges. But we're really seeing things developing enormously quickly. Over the last couple of weeks, all of the major hyperscalers and data center companies are talking about data centers in space. And the thesis is exactly the same as for space solar power, that really, actually, if we want to harness long-term energy security, the sun is our long-term energy source, and you can harness that far more effectively up in space. So even at the Tesla shareholders meeting, Elon Musk was talking about this now. So it's really developing incredibly quickly. So what we're developing with space solar is our Cassiopeia concept, which you can see orbiting high above the Earth there. One of the challenges with space solar power is, as you go around, orbit around the planet, the angle between the sun and the Earth changes. So many designs have a heavy rotating mechanical joint, which is a single point failure. So we can beam in 360 degrees, a bit like a lighthouse, but with no moving parts. And that means we use all the parts all the time, which massively lowers the mass and hence increases the ultimate performance. You can see the satellite there, the helix structure. If you imagine a spiral staircase is in the middle, and that's what does the wireless power transmission. So you're putting your panels up in space for a couple of reasons. First, you see the sun all the time. Secondly, certainly in high latitudes, you get 13 times more energy on those panels compared to panels on the ground. That's what really drives the economics. Given the heritage of wire and the sort of nucleus in Canada, I think also worth highlighting that these systems are assembled in space. They're large structures. Our commercial systems range from about 200 meters diameter to over a kilometer. And Canada is probably the world leader in space robotics. And given that, plus some of the opportunities and challenges around providing power for northern regions, it's obviously an important thing for Canada to be working towards. Then we convert that up in space into high frequency radio waves. We actually use Wi-Fi frequencies and transmit that in a very low power density beam down to a receiving antenna on Earth. You can see it there. It's a it's a transparent mesh-like structure, so you could not in the Arctic, but you could in principle grow crops underneath it, overlay it over a data center, stick it over a terrestrial solar farm, those sorts of things. And what you get is baseload power at $10 per megawatt hour, scalable. So this is mass producing mobile phone electronics and putting that up in space. That's what gives you your mass production economics. It's sustainable, about half the carbon footprint of terrestrial solar, and it's incredible flexibility. From a high Earth orbit, you can see a third of the Earth's surface and instantaneously switch the beam to points of demand, which really allows you to optimize the grid internationally. So just to bring it a bit more focus onto the Arctic and high latitudes, you can see here some different orbits. So John showed a geosynchronous orbit. And our systems, our baseline gigawatt scale systems, are also in a geosynchronous orbit. But if you look at a geostationary orbit, which is the horizontal line, you can see that stays constantly above a point on the planet. Great for many latitudes. But you can see a third of the Earth's surface and instantaneously switch the beam to points of demand. But as you go to higher latitudes, the beam starts to spread. You can see a low Earth orbit there, the tight pink line going vertically around the planet, and then the highly elliptical orbits. They're both brilliant for high latitudes. And one of the nice things is that as you go closer to the planet in the low Earth orbit, for example, your systems can become much smaller. So actually, the roadmap for space solar and many space solar power companies starts with low Earth orbit products that would actually be ideal for high latitudes. So you can see here just an image showing that, you know, as you go in a low Earth orbit, as the planet's rotating underneath, for most points on the planet, you see that point maybe once, possibly twice a day, but the polar regions you see very regularly, which allows you to deliver. It is intermittent power, but you can deliver significant power. So you're seeing here we're putting down megawatts every time we pass over, and you put in some battery storage, and you can average that out to really useful power levels for polar regions and high latitudes. So our product family has three main products. Merlin, which is our low Earth orbit system, where we're looking at hundreds of kilowatts from a low Earth orbit. Eagle's our gigawatt scale system from a geosynchronous orbit, and Kite is from one of those highly elliptical orbits and can deliver anything from 30 megawatts up to much higher than that. So what the nice thing I think John touched on, these are entirely arbitrary, flexible sizes in terms of what can actually be delivered. Making great progress. So we've done about $6 million of engineering work, got a really tight subsystem level design. We've demonstrated our 360-degree wireless power beaming, and also have a prototype for our in-space robotic assembly technology. And we've had the privilege of working with both Reykjavik Energy in Iceland around delivery of baseload power, and British Antarctic Survey around delivery of power for polar research stations, and really considering how we can provide that sustainable, environmentally responsible power to help that scale. And delivering in polar regions isn't without challenges. It's a harsh environment. You've got weather intermittency for other renewables. You need to clear off ice and snow in some cases, and obviously there's big maintenance costs and others. So if you can provide space-based solar power, then if you can address that by providing predictable energy generation all weather, resilience to the sort of snow and drifts, as you can engineer the rect tenor to be resilient to that, and then provide battery storage to provide continuous power, we can really start to provide much greater levels of power to high latitudes and to Arctic and Antarctic regions. So as that activity grows in those areas, how can we, as the space solar power community, really start to deliver additional power to help that activity grow? Here's what AI thinks a rect tenor might look like, but the point is that we can engineer the rect tenor to really be resilient to many of the conditions that are likely to be experienced in the Arctic or other regions. So it's got really high potential, and we're very excited to work with those that might be interested. So, you know, the headline is that much like the absolute transformation we've seen in communications, the future of power is also wireless. And as space solar power businesses develop from low Earth orbit to geo and highly elliptical orbits, we can grow alongside the power demands of northern regions, of polar regions. We're really excited to work with anyone that wants to work towards a sustainable, environmentally responsible, bright future in those areas. I've got a video I could show, but I think I've probably hit the boundaries, so I will stop there, I think, Heather, unless you want me to carry on. Heather?
You're welcome to carry on to finish up this final point. It's really fascinating, and we're fine for time. We're also very keen to hear from Dr. Karen, but it would be wonderful for you to conclude this point. So don't worry at all.
Great. Well, I mean, it's just going through a video which hopefully just shows things a bit more visually than some slides in terms of the hardware, what we're doing, and actually it will also show some of the beaming from space. So this is the assembly aspects. So how we assemble the satellites up in space, and then see a nice little image of the power beaming in space as well, which just perhaps brings it to life for people in their heads. There you go. I'll stop it there.
That's fantastic. Thank you so much. That's really, yeah, really compelling, really comprehensive. I've really learned a lot from that, and it was very strikingly presented. So thank you so much for that contribution, and I'm sure it will generate a lot of very interesting questions after we hear from our final speaker. So now let's go to Dr. Karen Hinze. Are you all set and ready? It would be wonderful to hear your contributions, and then we'll go into the question and answer session.
Thank you so much, Heather. And thank you to WIRE, and thank you to the Icelandic Arctic Cooperation Network. As I had mentioned in the prep, my group has a lot before, when meetings were in person in Toronto, a lot of members of my group have been there, and I've actually also won prizes. The women in my group have won prizes from WIRE. So thank you for your support over the years. And I just want to say that I'm presenting from the traditional lands of the Algonquin Anishinaabe Nation in Ottawa. So I'm going to talk more a bit on components, since I do work in systems, but I do a lot of work in components. I'm part of an institute for quantum technologies, and we fab chips, and I'm really happy to have heard, you know, John and Sam's talk, because I'm very impressed by doing whole systems as well. Now I work on systems, but not always me. I help out, but we always collaborate with companies or do spin-offs from the group. Our group does a number of things, and I'm going to talk a bit about a few topics that I'm all going to bring together at the end that have to do with the Arctic and with power beaming. But our group works on essential elements of sort of present generation and next generation power beaming systems, being them solar cells, being beaming technologies, and also I'm going to talk about an emerging, what I work a lot is in photonics, so emerging photonic power, which uses lasers instead of RF. And as well, we work a lot on how light is transmitted through clouds, as well as sort of development of smart grids as well. So just because I have one of my, I've had many students who've worked on the Arctic, but I had one that came out recently. And if you're interested, there's this thesis has 7 peer-reviewed articles on different uses for photovoltaics of the Arctic. And I took a few of Aaron Tonita's slides just to show a little bit sort of Arctic where we're at for electricity generation now. I know we heard a lot about cost. We heard a lot about how you can sort of see a lot from satellites or beam down power from satellites. But if we start here, what we can see here is that most of our electricity is generated from fossil fuels in the north, and it's very expensive. And the more northern you are, usually, except for a few locations where it's hydro, it's a lot of diesel being brought in by boat or plane, extremely expensive. And this thesis was a lot on solar. So I've got solar installation maps here. And what we can see is in the summer, there's we could go just with solar. Now, solar and batteries or other forms of storage and some hydros for some locations. But in the winter, and there's a lot of people who live in the Arctic in the winter and a lot of needs also for all kinds of uses. There is not a lot of solar insolation here. When it's white, it means there's really nothing coming at those times. And another thing that I want to talk about is really sort of surface temperatures. And they do vary. If you can see here, we're looking at different, the Arctic is about this location is here to the center. What we can see here is the surface temperatures actually vary quite a bit over the year. So there's a lot of sort of one of the issues with any type of insulation is change to the local permafrost. And the need for structures that do not affect the permafrost too much, because when you're talking about energy, there's usually a release of heat. I said I do a lot of work in photovoltaics. I'm going to get to photovoltaics in space, but first of all, just for the Arctic, there are many geometries, and usually the more northern you are, the more vertical you'll be, because you want to have structures that do not accumulate slope, although with wind sections, you can still get snow. So a lot of the new infrastructure, vertical, building integrated, or A-frame are better technologies, and not necessarily, you can of course use with trackers, but trackers usually you would have to have a crew that would be able to go there should there be issues with the tracking system. So our group we've published a lot on trackers, but in the last 2-3 years, I've really started being a big fan of these more east-west facing tracking system, and our group has a bunch of papers on that. This slide here talks about reliability, which is extremely important in Arctic regions. Are these systems, and if there's power beaming from RF and there's power beaming from let's say from lasers, you need installations that are reliable. So if we look at the data that we have from long-term installations, and you can see these are not large installations, but they have been instrumented and now have years of data. What we can see is that actually the degradation rates of these systems is better than the spec sheets that all the vendors sold. So we have equivalent, we can say for a nice installed system, we have equivalent reliability than things that are more south, more southern locations. Now, all these systems that I showed are silicon, and actually these big, when we talk about big deployments in space, it might be silicon, that will be deployed. And these are sort of silicon panels that I took from a stock photo. But most of the photovoltaics that are deployed right now in space are for long-term deployments anyways, are what are called 3-5 semiconductors. And here I put a big triangle here to show you where we are in efficiencies. So usually the capture of these systems are just below around 38%, 37 to 38% of what's deployed. And our group has done a lot of work on these types of cells over the years. And the newer technologies, if this technology wants to be used for power beaming, costs must go down. And there's a number of ways to do that. And we've published a number of papers. I've told you I'm going into a lot of technical terms, but a lot on how to have a lot of lower cost substrates and also faster deposition times. The faster deposition times it's work we did with NREL in the US. And here just we talked about a bit of robotics. Our group has done work on sort of space panels for applications. Now the concept of free space optics, what we saw from John and Sam is using wireless, which has a fairly high efficiency, is a mature technology. So it should be what should be deployed in the short term. But as we go in the longer term, a lot of things that are deployed on systems in the future, in the very near future, is a photonic telecommunication system. So then there's a lot of investment in the telecom field to have smaller components. And photonics, because of the wavelengths, the wavelength is smaller than microwaves, you can have smaller components. So that's the big advantage. And a lot of the deployments at this time are for applications for free space optics, but at shorter distances or underwater, because you have some wavelengths that can transport power for a very long distance. Now, the advantage is that it can be the main advantage, I'll just say, to microwave is really more compact. And if there's any questions, I can answer them. I just want to talk here. I had a slide when I was preparing yesterday about just markets, and there's no real market. I couldn't find any data on the markets for space beaming. And if you look, these markets are very, the sort of commercial components are coming out now. We've done a lot of work on improving efficiency of the receiver. They are multi-junction, single or multi-junction receivers for optical space delivery. And in the last few years, we've done a lot of work on eye-safe wavelengths. And the papers that we've published in the last 2-3 years are all based on eye-safe applications, that could be applied for space to ground. Other work that we've been doing is developing software. So one of the great things with microwave is there's some wavelengths that are great for transmitting power through the clouds. So I didn't have time to put in a sort of what are the windows of transmission, but we have some also in optics where in the eye it might look cloudy, but power goes through the clouds anyway. So one of the things is that we've developed a software that's being transferred to commercial uses for multiple wavelengths for very large bandwidths that can be used to model sort of how much power will be deployed and also map it with sort of real-time data. So that's an innovation that our group is spinning off right now. So on this note, I'm gonna stop the talk. And I'm very much looking forward to questions on the different aspects of and the challenges of and the excitement around power beaming to the ground from space.
Thank you so much for that, Dr. Hinson. That was really, really insightful. And it's really fascinating to hear all the work that you've done. I feel really honored that we have such experts in the same online space to get all of these perspectives. So if this works for everyone, unless any of the speakers have anything else they want to briefly add, I thought we'd move into the portion of the webinar in which I, as the moderator, ask some questions to the panelists, some of which will be, I'll start off with the ones which are for all of the speakers to respond to in turn. Then there may be a few specific ones, and from there we'll go into the Q&A session from all of those who are listening in, and any questions that they might have. So the question I wanted to ask first and foremost is quite broad, but will hopefully open up some interesting responses, which is what you foresee as being the hardest problem needing to be solved for space-based solar power to be fully realized. What would you yourself say would be the most significant challenge? I've been doing quite a lot of reading in the last few weeks about potential challenges, and I'm very interested in my perspective. A lot of the work I do is on space debris, so that's what kind of comes to the forefront of my mind. But that's coloured by my own by my own kind of lens on contemporary space issues. So I'm really keen to hear. Perhaps we could do it in the order in which we were meant to do this week. So John, and then Sam, and then Dr. Hinze. What you would consider to be the most significant challenge?
So thank you, Heather. I'm going to set aside for a moment the biggest challenge, which is persuading decision makers that this is now a technology area that is ready to move forward, and that they should start writing major checks. They're writing checks for fusion and all sorts of things, but not yet for space solar power the way they should. So I'm going to set that one aside as just a given, and speak to the technical issue. Everybody talks about wireless power transmission is super hard. Wireless power transmission was first demonstrated in the 60s. And there have been tests over and over. I've been involved in 7 separate demos of wireless power transmission over the years. That one is actually not that hard, although it's essential. The one that is, to me, the hardest is making the transition from structural systems on the order of tens of meters to structural systems on the order of thousands of meters, and the associated deployment, structural interconnections, assembly, robotics, and doing that in a way that is affordable and cheap, like you would do with prefabbed structural systems or warehouses and here on the Earth. The how do you put something together and do it quickly and affordably and reliably and repeatably, that is on the order of kilometers in scale? I think it's doable, but it has not yet been proven, and it represents an area of risk in the minds of prospective investors, whether government or private.
That was very, very, very insightful answer. Yes, and very persuasive. I was already very persuaded, but it was very persuasive answer. Sam, I'd really love to hear your perspective on this.
Thanks, Heather. I mean, that's I'd agree with John. I mean, I think the sort of counter on the robotics, it's applying terrestrial robotics technologies in space. So in that regard, there's a pretty good level of maturity there too. I think regulations obviously a long pole in the tent. We've done a lot of work bringing the key regulators together, and I think the kind of message from there is that with political will, this is all absolutely doable. Just to talk to your space debris sort of concern, Heather, I mean, we're consciously using low debris orbits, and then the systems are unlike anything that's been put in space before. They're ultra thin. I mean, they're like thick paper, thin card in terms of thickness. So if you throw a stone through it, it tears rather than shatters. And so I think that
that's really important.
You design to avoid debris. I mean, again, sort of rabbit hole on that, but the way we use space today is slightly crazy. And actually, if you look at the way everything's evolved economically in everything from the microscopic to the macroscopic, it's about bringing stuff together. It's about clusters and nodes and things like large structures will, I think, do the same thing for space as has happened terrestrially, which can hopefully be a good thing.
Definitely.
But actually, just to say, don't think any of us talked about timescales, and I think it's really worth highlighting this is happening now. People are talking about commercial power within 5 years, and with some of the big players I alluded to at the start of the talk now starting to engage, this is going to accelerate really, really quickly.
Fantastic. Wow, that's a fantastic answer. And I should apologize if in my phrasing of my question that I implied a kind of speculativeness, because I meant the challenges between now and this becoming a reality, but that it is certainly to become a reality. So yeah, thank you for that. And I was really, really interested to hear your answer on the space debris issue. And so beautiful to hear that being factored in to the design as well. That's really fantastic. Wonderful. Dr. Hinzer, it would also be wonderful to hear your contribution.
Thank you. I agree with John and Sam, and I'll add a few other things. First of all, well, for energy projects, these are large scale energy projects. So a lot of it is who owns, ownership, and risk. And space is still considered risky, although we've had satellites deployed for a long time, but not necessarily energy satellites. And energy there's a lot of money, but there's also risk assessment. So I think as these technologies, and I think like for me, wireless power beaming is like an established technology. And I look at a lot of other things, everything's very established. And it's more just the concept of larger and not being able to drive to it, not being able to use a boat and get to the island where it is or something like that. And for power, usually you want multiple sources. And I mentioned we already have energy sources for the north, so this is an add-on, and there's storage now is advancing. So even let's say all you need is duplication. So you need to have multiple. You need to have an extra few systems there that are there for if something fails. So it's usually more investment, just ensuring that you have all this additional power available, which is how energy operators work all the time. Though you always want to have reserve power. So as long as systems are designed that way, I don't see a technical issue with the deployment.
Yeah, no, that certainly makes sense, and it's very persuasive. And please don't feel that there was any skepticism baked in to my question whatsoever. I'm really fascinated
and Heather, just one thing also with energy, it's always energy acceptance, from governments and from users, and then also from the land, the people on the land. So it's very important it's great to talk about great technology, but really who's the owner, who's making the money off of it, and is it beneficial for the local community?
Yeah, absolutely, which are very, very important factors. Okay, the next question that was come from the hive mind, partly from myself and from others. You may have slightly answered, which is honing in on the technological bottleneck. Like what do you see as and we've talked about, for instance, these broader issues of political will or of coordination. But to hone in just on the granularity of the technological aspects, what do you see as being technological impediments to full-scale deployment, or is this not a concern? So happy to hear. I'm happy for us to always go in the order that we went with John, Sam, and Dr. Hinzer, or whatever anyone can hop in.
So there are more than a dozen organizations all racing to catch up with what SpaceX has already accomplished. Hundreds of launches a year with a largely reusable booster, and moving forward to a fully reusable two-stage orbit launcher. And so lots and lots of players are all working on fully reusable two-stage to orbit launchers. And so it's reasonable to anticipate, given where the market is and given where the industry is in the countries, low-cost Earth-to-orbit transportation is just going to be true. Now, in general, only SpaceX, with its refillable second stage concept, is currently working on really affordable in-space transportation. How do you go from low Earth orbit to the deployment orbit, whether it's GEO or GSO or MONIA or elliptical, sun synchronous, whatever it is? How do you go from a simple LEO to wherever you're going to deploy these very large systems? And so I think that, setting aside the question of assembly and construction, which I talked about already, the technical challenge that has to be resolved is also an industry challenge, and that's very low cost transportation from low Earth orbit, from wherever the Earth to orbit system drops you off, to wherever you're going to be deploying your space solar power system. that segment. It's probably reusable. It's probably either an earth-based solution like the ship refilled with some of whatever system it is, or it's probably solar electric. So there are a few options for the deployment. But that's got to be industrial scale in order to move forward with the launch and deployment of thousands of tons of equipment per space solar power system.
Yeah, I think that's bang on, John. I mean, obviously, sometimes need to sort of factor some of the things that Elon Musk puts out in the world, but he's talking, I think I saw last week, he's saying 100 gigawatts per year within 4 to 5 years' time. Even if it's an order of magnitude less than that, it's, you know, it's moving in. Yeah, this starts to make space solar power economic. I mean, you know, it's fascinating that all those data center companies are talking about orbital data centers, and the truth is that that's great, and hopefully they'll work. That would be beneficial to the planet. But if the economics works for orbital data centers, by the time that works, because they're much heavier systems, space solar power will be the cheapest form of power for the planet. So the kind of path dependency, the sort of momentum that's generated at the moment is really strong. Technically, Heather, I'm not going to pull out any of the technical challenges other than to say it's an engineering thing, not a physics thing. All the physics is completely understood, and it's about engineering the economics. So again, from a space solar perspective, if we built one of our satellites today using today's technologies, we know that we could have levelized cost of electricity as good as offshore wind, but base load. But we've got pathways through some of the developments that Karen and others will be aware of with the super light PV, you know, taking the substrate off the back, it improves the radiation performance, actually self-heals in space. You can get to well below terrestrial solar. So it's a really exciting space.
Thank you so much for those contributions. And Dr. Hinze, did you have anything that you wanted to add?
Just looking at the time, so I think they're covering it, and if we look at other things from space if you look at technologies that have been deployed in space, the biggest one that people have seen the effects is, you know, really because of the LEO satellite deployments is very cheap internet everywhere. No, and this is the kind of thing that can this is space-based power beaming is also this type of technology that transforms a market that then people will say, well, we don't have a need for it. But then when it exists, everybody adopts that technology extremely rapidly. So I can see that like we do a few demonstrations and then everybody will want to have it. No, so it's sort of these transformative technologies. Now, and we have to think we're replacing diesel. No, that is a really expensive diesel. No, the most expensive diesel in the world. No, because it's brought in by boat or flown in. No, that you're looking at, and then opens up new sort of new industries. No, where there's maybe no industry or very little industry. Okay, so it's a lot, the social change, we have to also prepare for the social change, but people, when there's an inexpensive technology like inexpensive electricity, will have a tendency to use it and better their lives.
Fantastic, very, very good point. And I'm also, you know, on this type, I wanted us to cover as much as possible in the time that we have. So now I have a question that sort of anchors this discussion in the work of Friedrich and Maya, and which brought us here today, to do with the specificities of the Arctic. And this is something that I've had, you know, at the forefront of my mind whilst talking all of this through. You know, Sam saying, you know, why now? But also this question of like, well, why here in the Arctic region? So the question I had on this topic is, how do you evaluate the feasibility of space-based solar energy regulatory environmental stresses such as the extreme cold or the ice and snow in the Arctic region? I mean, to what extent do those additional variables provide, you know, produce extra stresses, which then which require like recalibration, whether from an engineering perspective or in terms of other practices.
Yeah, I think one of the sorry, John, did you want to come in?
Just one quick point. So that in just comparing it to other options, the nice thing about microwave wireless power transmission is that the receivers can be extraordinarily efficient. So the conversion of incoming energy, RF energy, to electrical voltage can be on the order of 90% or so. Unlike photovoltaics, which are on the order of 25 or 30%, even for really good terrestrial power. So the amount of waste heat that is re-radiated to the ground, to the permafrost, can be exceptionally low for a space solar power receiving site. And I think that would, the studies have to be done, but that would allow significantly less local stress than other solar approaches. Sorry, Sam.
Not at all, John. I think that's really spot on. I mean, the things I was going to say, I mean, firstly, the rectennas are really simple things. I mean, they basically look like crossed wires on poles. So it's a mesh, but really lightweight. So firstly, the transportation costs to get it there, very effective. Second, they're super simple, very basic electronics. So in that context, there's not much that can go wrong. And then it's an engineering. It's about how you engineer it. So it's got a very small horizontal cross section, so you're not likely to suffer from drifting and things like that. And then I think John's bang on with the sort of conversion efficiencies, but actually that's something that can also be played with. So you might want a little bit of heat, so it actually keeps there might be benefits to that. I mean, and I think the headline is that this is a great option that we can engineer it so that it works for specific applications.
Heather, I'd like to just add that, if we're comparing to diesel generators, they're noisy, they smell, they require maintenance. They have an environmental impact, and you have to transport it there, and you're transporting it using carbon emitting sources, and some extremely highly polluting carbon emitting sources, especially if you're flying it in. No, so, and usually the fly-ins are not on the most, it's not the most recent plane. They're older planes usually, older transport planes, and for boats as well, older transport boats. So there's a lot of emissions just to get to there. In this case, everything is emissions free. No, so yes, there may be some impact on the site, but if you look at you do a comparative, and I should write a paper on that, comparative impact with present technologies for equivalent amount of power generated, this is most likely orders of magnitude cleaner. No, cleaner and less impact to the environment.
Thank you so much. I have to jump in. It pains me to say that this is all the time we have today. It beggars belief that an hour is already gone, because it's like I've been exposed to all this science fiction. It's truly fascinating. So I would just like to take the opportunity to end this fascinating discussion by first thanking our wonderful speakers for their insightful presentation. So thank you, Sam, thank you, Karen and John. And of course, thank you to Heather, our moderator, for facilitating this fascinating dialogue. So I'd just like to quickly mention, so we will be subsequently sending out a survey to attendees. So for those interested in this series, it would be much appreciated if you took the time to provide us with your feedback. So to conclude, I thank you all yet again on behalf of the ICN and WIRE for your attendance, and I look forward to discussions ahead. So thank you, everyone.